So, good day everyone. Today I am going to discuss the uncertainty management in rule-based expert systems. So, the topic that we're going to discuss under the uncertainty management are what is uncertainty, basic probability theory, Bayesian reasoning, bias of the Bayesian method, certainty factors theory, and evidential reasoning, and summary. What is uncertainty in expert systems? Uncertainty can be defined as the lack of the exact knowledge that would enable us to reach a perfectly reliable conclusion, according to Stefano and Sage 1987. So basically, uncertainty refers to a situation where we don't have complete information. So if we are uncertain, then we are not entirely sure about the outcome or correctness of the decision. Classical logic permits only exact reasoning. It assumes that perfect knowledge always exists and the law of the excluded middle can always be applied. So, classical logic is a system of reasoning na nag-assume po ng every statement is either true or false and that there is no middle ground. So, it means na if ang statement is true, then yung negation po niya or kabaliktaran must be false and vice versa. In other words, there is no third option, such as a statement being neither true or false. So for example, if A is true, then A is not true. And if B is false, then B is not true. What are the sources of uncertain knowledge in expert systems? In general, we can identify four main sources, and those are weak implications, imprecise language, unknown data, difficulty of combining the views of different experts. Weak implications. Rule-based expert systems often suffer from weak implications and vague associations. Domain experts and knowledge engineers have the painful and rather hopeless task of establishing concrete correlations between if and then parts of the rules. Rule-based expert systems are not always able to make accurate predictions because the knowledge they're based on is often incomplete or imprecise. Ang problem po with the rule-based expert system is kung yung if part of the rules are often vague or imprecise. So kagaya po ng example last time na if nilalagnat yung isang tao, then may COVID ka agad. We're in fact po na mayroon pong ibang dahilan kung bakit po siya nilalagnat. Therefore, expert systems need to have the ability to handle vague associations, for example, by accepting the degree of correlations as numerical certainty factors. Imprecise language. Our natural language is inherently ambiguous and imprecise. We describe facts with such terms as often and sometimes, frequently and hardly ever. As a result, it can be difficult to express knowledge in the precise if-then form of production rules. So the words that we use in natural language can have multiple meanings or can be interpreted in different ways. For example po, yung word na often, para sa akin is meron siyang ibang meaning and sa inyo din ay meron po siyang ibang meaning. So, this ambiguity can make it difficult to express knowledge in the precise if-then form of production rules. Example, gamitin natin yung often in a fact. So, if it often rains, then take an umbrella. So, di ba nagiging ambiguous siya or malabong maintindihan dahil sa salitang often, which can have multiple meanings. However, if the meaning of the facts is quantified, it can be used in expert systems. So, for example po, pwede po tayong mag-assign ng value na 0.9 to the fact, it often rains in Manila. So it means that we are 90% confident that it rains in Manila most of the time. By quantifying the meaning of facts, we can make them more precise and easier for computers to understand. And in 1944, Ray Simpson asked 355 high school and college students to place 20 terms, like often on a scale between 1 and 100. In 1968, Milton Hackle repeated this experiment. So this table 3.1 shows the quantification of ambiguous and imprecise terms on a time-frequently scale, a study conducted by Ray Simpson in 1944 and by Milton Hackle in 1968. Unknown data. When the data is incomplete or missing, the only solution is to accept the value unknown and proceed to an approximate reasoning with this value. Combining the views of different experts. Large expert systems usually combine the knowledge and expertise of a number of experts. However, experts have contradictory opinions and produce conflicting rules. To resolve the conflict, the knowledge engineer has to attach a weight to each expert and then calculate the composite conclusion. So, this weight refers to the degree of confidence. The experts with higher weights are given more weight in the decision-making process. No systematic method exists to obtain weights. So basically, the knowledge engineer has to rely on their own judgment to decide how much weight to give to each expert. An expert system should be able to manage uncertainties because any real-world domain contains inexact knowledge and needs to cope up with incomplete, inconsistent, or even missing data. A number of numeric and non-numeric methods have been developed to deal with uncertainty in rule-based expert system, according to Bhatnagar and Canal 1986. So, the basic probability theory. The concept of probability has a long history that goes back thousands of years when words like probably, likely, maybe, perhaps, and possibly were introduced into spoken languages, according to Good 1959. However, the mathematical theory of probability was formulated only in the 17th century. The probability of an event is the proportion of cases in which the event occurs. Probability can also be defined as a scientific measure of chance. So, the probability can be expressed mathematically as a numerical index with a range between 0 and absolute impossibility to unity and absolute certainty. Most events have a probability index strictly between 0 and 1, which means that each event has at least two possible outcomes, which are favorable outcome or success and unfavorable outcome or failure. So the probability of success and failure can be determined. So probability of success is equals to the number of success divided by the number of possible outcomes, and the probability of failure is equals to the number of failures divided by the number of possible outcomes. So therefore, if S is the number of times success can occur, and if is the number of times failure can occur, then probability of success is equals to P is equals to success divided by success plus failure, and probability of failure equals to Q divided by failure equals to failure divided by success plus failure. So we have observed that there is a symbol P and Q. So P represents the probability of success and Q is the probability of failure. So when we add these two values, their sum is equals to 1. So kung nagke-question po tayo kung bakit po nagiging 1 siya, because the probability of success is 1/2 and the probability of failure is 1/2. So this satisfies the equation P plus Q is equals to 1. Suppose if we throw a coin, the probability of getting a head will be equal to the probability of getting a tail. In a single throw, success is equals to failure is equals to 1. And therefore, the probability of getting a head or a tail is 0.5. So, for example daw po, when you toss a coin, there are two possible outcomes, which is the probability of getting a head is equals to the probability of getting the tail. So, the formula po, S is equals to F is equals to 1 refers to the number of successful outcomes and the number of unsuccessful outcomes. So the value of S is equals to 1, so as well as the value of S is equals to 1. So we have here the formula that calculates the probability of getting a success, which in this case is getting a head. So since the value of our S is equals to 1 and our F is 1, so 1 divided by 1 plus 1, so we have 1 half. 1 divided by 2, so our probability is 0.5. So it means that there is a 50% chance of getting heads when you toss a coin once, and the probability of getting tails is also 50%. Conditional probability. Let A be an event in the world and B in another event. Suppose that events A and B are not mutually exclusive, but occur conditionally on the occurrence of the other. The probability that event A will occur if event B occurs is called the conditional probability. So conditional probability is the measure of probability of an event occurring given that another event has already occurred. Conditional probability is denoted mathematically as probability of A given B in which the vertical bar represents given. So ito po. And the complete probability expression is interpreted as conditional probability of event A occurring given that event B has occurred is equals to the number of times A and B can occur divided by the number of times B can occur. The number of times A and B can occur, or the probability that both A and B will occur, is called the joint probability. So joint probability refers to the probability of two or more events happening together. So in this case is event A and B. It is represented mathematically as probability of events A and B both occurring. The number of ways B can occur is the probability of P and P, probability B. So we have here the equation. Similarly, the conditional probability of event B occurring given that event A has occurred. So this equation represents the conditional probability of B given A, which is similar po sa dito na equation po. Pero makikita po natin na niswap po yung A and B. So it's the proportion of times B and A both occurring divided by the total numbers of probability A. Hence, this equation simply rearranges the equation before itong equation po. So, it shows that the joint probability of both events B and A happening can be found by multiplying that event A has happened by the probability of event A. So the joint probability is commutative. So it means that the probability of A and B occurring together is the same as the probability of B and A both occurring together. Therefore, probability of A and B occurring together is equals to the probability of B given A multiplied by probability of A. So we will substitute this last equation into this equation. So after substituting it, so it will yield into a Bayesian rule. So this is the Bayesian rule where the conditional probability that event A occurs given that event B has occurred is equals to the conditional probability of event B occurring given that event A has occurred multiplied by probability of event A divided by probability B. The concept of conditional probability introduced so far considered that event A was dependent upon event B. This principle can be extended to event A being dependent on a number of mutually exclusive events, B1, B2, up to Bn. The following set of equations can then be derived from equation. So in this equation, or when combined, the sum from I is equals to 1 up to n of the joint probabilities of each event A and each event Bi is equals to the sum of I is equals to 1 up to n of the conditional probabilities of A given each event Bi multiplied by the probabilities of those event Bi. So if the occurrence of event A depends on only two mutually exclusive events, example, B and not B. So we have this equation where we have this equation. So where the symbol is the logical function not. So similarly, we have probability B is equals to probability of B given A multiplied by probability A plus probability B given not A multiplied by probability not A. So, di ba nakikita po natin na same lang po sila ng equation pero both A and B are being swapped lang. So, this equation, we will substitute this equation into the Bayesian rule. So, di ba po ito po yung Bayesian rule natin. So, after substituting it to the Bayesian rule, so we have now this equation. So, Bayesian reasoning. Suppose all rules in the knowledge base are represented in the following form. If E is true, then H is true with probability P. So kung kanina po is yung mga rule po natin is ito lang, yung if and then, so ngayon is with probability P na po siya. So this rule implies that if event E occurs, then the probability that event H will occur is P. In expert system, H usually represents hypothesis and E denotes evidence to support this hypothesis. So, yung equation po natin last will be replaced with H and A, which A represents as evidence and H is the hypothesis. So, we will now have this equation. So, where probability H given A is equals to probability E given H. So is the probability that hypothesis H being true will result in evidence E multiplied by probability H, where is the prior probability of hypothesis H being true divided by probability E given H. So sabi nga kanina, probability that hypothesis H being true will result in evidence E multiplied by probability H plus probability E given not H. So, is the probability of finding evidence E even when hypothesis H is false multiplied by probability not H, where is the prior probability of hypothesis H being false. In expert systems, the probabilities required to solve a problem are provided by experts. An expert determines the prior probabilities for possible hypotheses and P not H, and also the conditional probabilities for observing evidence E if hypothesis H is true, probability E given H, and if hypothesis H is false, then you will have this equation. Probability E given not H. So, users provide information about the evidence observed and the expert system computes probability H given A for hypothesis H in light of the user supplied evidence E. Probability H given A is called the posterior probability of hypothesis H upon observing evidence E. We can take into account both multiple hypotheses, hypothesis 1, 2, up to hypothesis n, and multiple evidences, evidence 1, 2, up to evidence n. But the hypotheses as well as the evidences must be mutually exclusive and exhaustive. So for the single evidence and multiple hypotheses, we can use this equation, while for multiple evidences and multiple hypotheses, we can use this equation. But this requires to obtain the conditional probabilities of all possible combinations of evidences for all hypotheses. This requirement places an enormous burden on the expert and makes his or her task practically impossible. According to Nang and Abraso 1990, in expert systems, conditional independence among different evidences assumed. So, to calculate the probability of each possible combination of evidence given each hypothesis, this is a very difficult task and time-consuming as there could be many possible combination of evidences and hypotheses. So the assumption is often made to simplify the task of calculating the probabilities of different hypotheses given a set of evidence by using this equation instead of those equations said a while ago that it can be only used for single evidences and for multiple evidences. But this can be used for to test many evidences with the given hypothesis. So, ranking potentially true hypothesis. Let us consider a simple example. Suppose an expert given three conditionally independent evidences, evidence 1, 2, and 3, creates three mutually exclusive, unexhaustive hypotheses, hypothesis 1, 2, and 3, and provides prior probabilities for these hypotheses, probability hypothesis 1, 2, and hypothesis 3, respectively. The expert also determines the conditional probabilities of observing each evidence for all possible hypotheses. So the table 3.2 shows the prior and conditional probabilities. So we will assume that we first observe evidence E3. The expert system computes the posterior probabilities for all hypotheses. So it says that we will compute for the first evidence. So we can use the formula for the single evidence with multiple hypotheses. So this equation can be used in finding the evidence tree with hypothesis. So the probability of hypothesis I given evidence 3 is equals to the probability of evidence 3 given hypothesis I multiplied by probability of hypothesis I divided by the sum of the products of the probability of evidence E3 given hypothesis K multiplied by probability of hypothesis K, where Rk is a variable used to index the different hypotheses, wherein it is 1 up to 3. So the 3 above shows the summation symbol indicates the upper limit or the number of terms we are summing. So our I is equals to 1, 2, and 3. So here, we're gonna test the hypothesis 1 given evidence 3. So our I, as said a while ago, is 1, 2, 3. So we'll start with I is equals to 1. So probability of evidence 3 given hypothesis 1. So our I is 1, so we have 0.6. And then the probability of hypothesis 1, so we have 0.40. 0.6 multiplied by 0.40, the product is 0.24. And then we will sum the three terms over here. So our index K is equals to 1. So our K now is 1. So the probability of evidence 3 given hypothesis 1. So we'll change this para hindi tayo maguluhan. So evidence 3, hypothesis 1, so we have 0.6, and then multiplied by the probability of hypothesis 1, so we have 0.40, plus, so our index K now is 2. So probability of evidence 3 given hypothesis 2, so our K is 2, so we have 0.7. And then multiplied by probability of hypothesis 2, so we have 0.35. And then our K now is 3. So probability of evidence 3 given hypothesis 3, so we have 0.9. And then multiplied by the probability of hypothesis 3, so we have 0.25. So if we add all the product of these three term, so we have 0.71, so we have 0.24 divided by 0.71, the answer is 0.34. Our I now is equals to 2. So we have 2. So the probability of hypothesis 2 given evidence 3. So probability of evidence 3 given hypothesis 2. So we have 0.7. And then the probability of hypothesis 2. So we have 0.35. So if we multiply, the product is 0.245. And then we'll just copy. So since same lang naman yung process kagaya po kanina, para hindi po tayo matagalan. So 0.245 divided by 0.71. So the answer is 0.34. And then our I now is 3. So our I is 3. So probability of hypothesis 3 given evidence 3 is equals to probability of evidence 3 given hypothesis 3. So we have 0.9 multiplied by probability of hypothesis 3. So we have 0.25. 0.9 multiplied by 0.25, the answer is 0.225 divided by 0.71 kasi same process lang po kanina. So the answer is 0.32. So makikita po natin na both hypothesis 1 and hypothesis 2 given evidence 3 is same lang po yung result. And then the probability of hypothesis 3 given evidence 3 is malapit-malapit po siya sa hypothesis 1 and hypothesis 2. Suppose now that we observe evidence 1, the posterior probabilities are calculated as using this equation wherein our I is equals to 1, 2, 3. So kung kanina po yung kinumpute po natin na evidence is for evidence 3, so now is madadagdagan po siya ng evidence 1. So our I is equals to 1. So our I is 1, so we have 1. Or I is equivalent to 1. So probability of hypothesis 1 given evidence 1 and 3. So A is equals to probability of evidence 1 given hypothesis 1. So we have 0.3 multiplied by probability of evidence 3 given hypothesis 1. So we have 0.6. And then probability of hypothesis 1. So we have 0.40. And then divided by, so since our index k is equals to 1, so our k is 1. Wait, change. So probability of evidence 1 given hypothesis 1, so we have 0.3 multiplied by probability of evidence 3 given hypothesis 1, so we have 0.6. And then the probability of hypothesis 1, so we have 0.40 plus, so our index k now is 2. So probability of evidence 1 given hypothesis 2, so we have 0.8. And then multiplied by probability of evidence 3 given hypothesis 2, so we have 0.7. And then multiplied by probability of hypothesis 2, so we have 0.35. And then plus our index now is 3. So probability of evidence 1 given hypothesis 3, so we have 0.5. And then probability of evidence 3 given hypothesis 3, so we have 0.9. And then multiplied by probability of hypothesis 3, so we have 0.25. So if we add them all, if we add the products, so the sum is 0.3805. And then the product of this one is 0.072. So 0.072 divided by 0.3805, the answer is 0.19. And then our I now is equals to 2. So hypothesis, our I is 2. So the probability of hypothesis 2 given evidence 1 and 3. So probability of evidence 1, hypothesis 2. So we have 0.8 multiplied by probability of evidence 3 given hypothesis 2. So we have 0.7. And then the probability of hypothesis 2. So we have 0.35. If we multiply them, the probability of hypothesis 2 given evidence 1 and 3 is 0.52. And then our I now is 3. So the probability of hypothesis 3 given evidence 1, evidence 3. So probability of evidence 1 given hypothesis 3. So we have 0.5. And then probability of evidence 3 given hypothesis 3. So we have 0.9. And then multiplied by probability of hypothesis 3. So we have 0.25. And their product is 0.1125, and then we will just copy since same process lang din naman. So when we divide them, the answer is 0.29. So na-observe po natin na probability of hypothesis 1 given evidence 1 and 3 has decreased po. And then probability of hypothesis 2 given evidence 1 and 3 is 0.52. So nag-increase po siya compared before. And then the probability of hypothesis 3 given evidence 1 and 3 has decreased then compared before. So after observing evidence 2 as well, the expert system calculates the final posterior probabilities for all hypotheses. So by using this equation, and our I is equals to 1, 2, 3, we will compute hypothesis I given evidence 1 and 2 and 3. So our I now is 1. So we have 1. Probability of hypothesis 1 given evidence 1, 2, and 3 is equals to probability of evidence 1 given hypothesis 1. So we have 0.3 multiplied by probability of evidence 2 given hypothesis 1. So we have 0.9. And then multiplied by probability of evidence 3 given hypothesis 1. So we have 0.6 multiplied by probability hypothesis 1. So we have 0.40. And then our index K over here is equals to 1. So equals to 1. So probability of evidence 1 given hypothesis 1. So we have 0.3. And then multiplied by probability of evidence 2 given hypothesis 1. So we have 0.9. And then multiplied by probability E3 given hypothesis 1. So we have 0.6. And then multiplied by probability H1. So we have 0.40. Plus, so our index K now is 2. So probability of evidence 1 given hypothesis 2. So we have 0.8. And then probability of evidence 2 given hypothesis 2, we have 0.0. And then probability of evidence 3 given hypothesis 2. So we have 0.7. And multiply probability of hypothesis 2. So we have 0.35. Plus, so our index K now is equals to 3. So probability of element 1, evidence 1 given hypothesis 3, so we have 0.5 multiplied by probability of evidence 2 given hypothesis 3, so we have 0.7, and then multiplied by probability of evidence 3 given hypothesis 3, so we have 0.9, and then multiplied by probability of hypothesis 3, which is 0.25. So if we sum or if we add these three terms, so we have 0.14355, so 0.0648 divided by 14355 is equals to 0.45. And then our I now is 2. So our I is 2. So probability of hypothesis 2 given evidence 1, 2, and 3 is equals to probability of evidence 1 given hypothesis 2. So we have 0.8. And then probability of evidence 2 given hypothesis 2. So we have 0.0. And then probability of evidence 3 given hypothesis 2. So we have 0.7. And then multiplied by the probability of hypothesis 2, so 0.35. So if we multiply them, the product would be 0. 0 divided by 0.14355 kasi po same setup or same process lang po kanina. So we just copy this para madali po. So 0 divided by 0.14355 is equals to 0. And then our I now is equals to 3. So probability of hypothesis 3 given evidence 1, 2, and 3 is equals to probability of evidence 1 given hypothesis 3. So we have 0.5, and then multiplied by probability of evidence 2 given hypothesis 3. So we have 0.7, and then multiplied by probability of evidence 3 given hypothesis 3. So we have 0.9 multiplied by probability of hypothesis 3. So 0.25. And then we will just copy again kasi same process lang din. So if we multiply them, the product is 0.07875. So divided by 0.14355, the probability of hypothesis 3 given evidence 1, 2, and 3 is equals to 0.55. So nakikita po natin na ang hypothesis 2 is equals to 0, so excluded na siya. And then hypothesis 1 and 3 has their own values, pero mas nakikita po natin na mas malaki po yung hypothesis 3 given evidence 1, 2, and 3. Bias of the Bayesian method. The framework for Bayesian reasoning requires probability values as primary inputs. The assessment of these values usually involve human judgment. However, psychological research shows that humans either cannot elicit probability values consistent with the Bayesian rules or do it badly, according to Borns and Pearl 1981 and Tversky and Kahneman in 1982. This suggests that the conditional probabilities may be inconsistent with the prior probabilities given by the expert. Consider, for example, a car that does not start and make odd noises when you press the starter. The conditional probability of the starter being faulty if the car makes odd noises may be expressed as: if the symptom is odd noises, then the starter is bad with probability 0.7. Apparently, the conditional probability that the starter is not bad if the car makes odd noises is, so may conditional probability po siya na sinasabi na kaya na baka po hindi po sira yung starter kung meron pong odd noises yung sasakyan. So, the probability of the starter is not bad given the odd noises is equals to 1 minus probability of the starter is bad given the odd noises. So the probability that the starter is not bad given the add noises is equals to 0.3. So kung nalilito po kayo kung saan nanggaling po itong 1, this 1 represents po the total probability of the two mutually exclusive events, which is the starter is bad and the starter is not bad when add noises are observed. Therefore, we can obtain a companion rule that states if the symptom is add noises, then the starter is good with probability 0.3. Domain experts do not deal easily with conditional probabilities and quite often deny the very existence of the hidden implicit probability. We would use available statistical information and empirical studies to derive the following two rules. If the starter is bad, then the symptom is add noises with probability 0.85. If the starter is bad, then the symptom is not add noises with probability 0.15. So to use the Bayesian rule, we still need the prior probability. The probability that the starter is bad if the car does not start, here we need an expert judgment. Suppose the expert supplies us the value of 5%. Now we can apply the Bayesian rule to obtain. So the probability that the starter is bad given the add noises is equals to, so kung nagtataka po kayo kung saan galing itong mga value na ito, so this came from the rule. So if the starter is bad, then the symptom is add noises with probability of 0.85. And then this 0.05 is the prior probability that the starter, so ito po, the probability that the starter is bad if the car does not start. And this 0.15, this 0.15, the starter is bad, then the symptom is not add noises. And this 0.95 over here comes from the probability that you will not observe add noises if the starter is bad. So 0.85 multiplied by 0.05, the product is 0.0425. And then 0.85 multiplied by 0.05, 0.15 multiplied by 0.95 when you add their product. So their sum is 0.185. Therefore, the probability that the starter is bad given add noises is 0.23. Therefore, the number obtained is significantly lower than the expert estimate of 0.7 given at the beginning. Certainty factors, theory, and evidential reasoning. Certainty factors theory is a popular alternative to Bayesian reasoning. Kaya po siya nagiging popular kasi it is simpler to understand even for people with no background in probability. More robust in uncertainty and more suitable for expert system because it is less computationally expensive. One example of the certainty factor theory was initially introduced as part of the MySyn expert system. MySyn was designed to diagnose and recommend therapies for blood infections and meningitis. In medical diagnosis, experts often express their beliefs or confidence in diagnosis in ways that are not strictly logical or mathematical consistent. This means that their knowledge is often qualitative in nature rather than being based on precise probabilities. Another challenge is the absence of reliable statistical data, so they've decided to introduce certainty factor. A certainty factor, a number to measure the expert's belief. The maximum value of the certainty factor was positive 1, definitely true, and the minimum is negative 1, which is definitely false. A positive value represented a degree of belief and a negative a degree of disbelief. For example, if the expert stated that some evidence was almost certainly true, a certainty factor value of 0.8 would be assigned to this evidence. So this was the uncertain terms and their interpretation based on MySyn. In expert system with certainty factors, the knowledge base consists of a set of rules that have the following syntax. If, which is the evidence, And then the hypothesis, certainty factor, where certainty factor represents belief in hypothesis H given that evidence E has scored. The certainty factors theory is based on two functions, measure of belief and measure of disbelief. So for the measure of belief, if the probability probability hypothesis is equals to 1, then it means that you're absolutely certain that the hypothesis is true, then the function returns 1. Otherwise, um, it will take the maximum of the probability hypothesis given A and the probability of hypothesis minus PH. So for example, the maximum of 1 and 0 is 1, so minus whatever the value of the probability hypothesis. So, and for the method measure of disbelief, so if the probability of hypothesis is equals to 0, then it will return 1. Otherwise, it would take the minimum of the probability of the hypothesis given E and the probability of hypothesis minus PH. So for the minimum, so we have 0 minus whatever the value of the probability of the hypothesis. So the values of method measure of belief and measure of disbelief ranges between 0 and 1. The strength of belief or disbelief in hypothesis H depends on the kind of evidence E observed. Some facts may increase the strength of belief, but some increase the strength of disbelief. In other words, the output of these functions falls within the range 0 and 1. This range often used in probabilistic context to represent degrees of belief or confidence. Kaya, kagaya po ng sinabi kanina, 0 means complete uncertainty, certainty that something is false, and 1 means complete belief that something is true. So to determine the total strength of belief or disbelief in hypothesis, the measure of belief and measure of disbelief are combined into one equation, which is the certainty factor. So we will consider a simple rule. If A is X, then B is Y. So an expert may not be absolutely certain that this rule holds. Also, suppose it has been observed that in some cases, even when the if part of the rule is satisfied, an object A takes on value X, object B can acquire some different value Z. So it says that the expert is not absolutely certain that this rule always holds. In other words, there is a chance that even if object A is X, object B could be Z instead of Y. The expert can associate a certainty factor with each possible value of B given that A has value of X. In this case, the certainty factor for B being Y is 0.7 and B being Z is 0.2. So if we have observed, if we add B is Y and B is C, so we have certainty factor of 0.9. So where is the other 10%? The other 10% of the time, it could be anything. In such a way, the expert might preserve a possibility that object B can take not only two known values, Y and Z, but also some other values that has not yet been observed. Thus, the certainty factor assigned by a rule is then propagated through the reasoning chain. Propagation of the certainty factor involves establishing the net certainty of the rule consequent when the evidence in the rule antecedent is uncertain. So propagated means that when a rule assigns a certain level of confidence or certainty to a statement, this level of confidence is passed along through a series of logical steps in a chain of reasoning. So this equation has been used for a single antecedent rule of certain factor of hypothesis H given evidence E. So it can be calculated by multiplying the certainty factor of evidence A with the rule certainty factor. So for example, if the sky is clear, then the forecast is sunny with a certainty factor of 0.5. 0.8, I mean. And the current certainty factor of sky is clear is 0.5. Then, so it says that the evidence is that the sky is clear is 0.5. And then the certainty factor is 0.8. So the certainty factor of hypothesis given evidence E is 0.4. So the result 0.4 according to table 3.4 would be read as it may be sunny. So kung natatandaan po natin sa based on the previous discussion na there are that the rule can have multiple antecedents, which are the conjunction or the disjunction. For the conjunction, which is the and, so for conjunctive rules, the certainty of the hypothesis H is established as follow. So the certainty factor of hypothesis H given evidence E1 and E2 up to evidence En is equal to the minimum of the certainty factors of evidence 1, evidence 2, and evidence N multiplied by the certainty factor. So for example, if the sky is clear and the forecast is sunny, then the action is wear glasses with a certainty factor of 0.8. And the certainty of sky is clear, so we have here is 0.9, and the certainty of the forecast is sunny is 0.7. Then, the certainty factor of hypothesis given evidence 1 and evidence 2 is equals to the minimum. So, our evidence 1 that the sky is clear is 0.9. And then the evidence 2, which says that the forecast is sunny, is 0.7 multiplied by the certainty factor, so 0.8. The minimum here for the two evidences is 0.7. So 0.7 multiplied by 0.8. So the certainty factor of hypothesis given evidence 1 and 2 is equals to 0.56. And the result 0.56, according to table 3.4, this conclusion might be interpreted as probably it would be a good idea to wear sunglasses today. For disjunctive rule, so we have the or. For disjunctive rules, the certainty of the hypothesis H is established as follows. So certainty factor of hypothesis H given evidence E1 or evidence 2 or evidence N is equals to the maximum certain factor of evidence 1, evidence 2, up to evidence N multiplied by certainty factors. For example, if the sky is overcast or the forecast is rain, then the action is take an umbrella. Certainty factor is 0.9. And the certainty of sky is overcast is 0.6, and the certainty of the forecast is rain is 0.8. So the certainty factor of hypothesis given evidence 1 or evidence 2 is equals to the maximum of certainty factor of evidence 1, which is that the sky is overcast, is 0.6, and the certainty factor of the forecast rain is 0.8 multiplied by the certainty factor 0.9. So the maximum between the certainty factor of two evidences is 0.8. So we multiply 0.8 by 0.9. So the certainty factor of hypothesis given evidence 1 or evidence 2 is 0.72. And the result 0.72 according to table 3.4, which can be interpreted as almost certainly an umbrella should be taken today. When the same consequent is obtained as a result of the execution of two or more rules, the individual certainty factors of these rules must be merged to give a combined certainty factors for a hypothesis. So suppose the knowledge base consists of the following rules. So imimix na po yung and or. So what certainty should be assigned to object C having value Z if both Rule 1 and Rule 2 are fired. So nakikita po natin na Rule 1 and Rule 2, so there are different evidences. Pero sa hypothesis po is nakikita po natin na then C is Z, and then sa Rule 2 naman po is C is C. So sometimes two or even more rules can affect the same hypothesis. How does an expert system cope up with this situation? So if we have two pieces of evidences such as A is X and B is Y from different sources, which are Rule 1 and Rule 2 supporting the same hypothesis, C is Z, then the confidence in this hypothesis should increase and become stronger than if only one piece of evidence had been obtained to calculate a combined certainty factor. We can use this equation. So for the first equation, so it is used when both pieces of evidences are positive. So kung both evidences are positive. So certainty factor of the combined evidence is equals to the certainty factor of the two pieces of evidence multiplied by 1 minus certainty factor. So, and then for the second equation, it is used when one or both pieces of evidence are negative. So, certainty factor of the combined evidence is equals to certainty factor to the sum of the certainty factor of the two evidences divided by 1 minus the minimum of the absolute values of the two certainty factors. And then for the third equation, it is used when both pieces of evidence are negative. So the certainty factor of the combined evidence is equals to the sum of the two pieces of the evidences multiplied by 1 plus certainty factor. So we assume that certainty factor evidence 1 and certainty factor evidence 2 is equals to 1. So pareha po siyang positive. Then from the equation, certainty factor hypothesis given evidence E is equals to certainty factor evidence multiplied by certainty. So the certainty factor of the hypothesis given evidence 1 is 0.8, and then the certainty factor of hypothesis given evidence 2 is 0.6. So from the equation, so yung equation po, sinasabi po natin na both positive po siya. So, di ba, if both positive yung evidences, then we would go for the first equation. So, certainty factor of the combined two pieces of evidences is equals to certainty factor of hypothesis given evidence 1, which is 0.8. So, dito po siya. And then plus the certainty factor of hypothesis given evidence 2, which is 0.6, multiplied by 1 minus certainty factor of hypothesis evidence 1, which is again 0.8. So the total is 0.9. And it shows po na there is an incremental increase of belief in hypothesis and also confirm the expectation. Sorry. And we will now consider a case when rule certainty factors have the opposite sign. So suppose that the certainty factor of evidence 1 is positive 1 and certainty factor of evidence 2 is negative 1. So from the equation, this one, we will get, so certainty factor of hypothesis given evidence 1 here is equals to 0.8. Kasi po, yung certainty factor of evidence 1 is positive 1. And then the certainty factor of hypothesis given evidence 2, so ang certainty factor of evidence 2 is negative 1. Multiplied by certainty factor, so we have negative 0.6. So kaya we will go with the second equation. Kasi sinasabi po na there is an opposite sign. So certainty factor with the combined certainty factor of the two evidences. So we have certainty factor 1, hypothesis given evidence 1. So ito po siya. So we have 0.8. and then plus certainty factor of hypothesis given evidence 2. So, di ba nakikita po natin na negative siya? So, since positive plus po siya dito and ito ay negative, so different signs po siya, so we will subtract. And then 1 minus the minimum of the absolute value of the certainty factor, 1 and certainty factor. So, 1 minus minimum. So, nagiging positive siya dito kasi sabi absolute eh. So, from negative, it would be positive. So, 1 minus minimum. So, ito po ang nangyayari. 0.8 minus 0.6 divided by 1. Ang minimum po dito is 0.6. Siya po yung mababa. 0.2 divided by 0.4. So, we have 0.5 and it shows a combine of, or in other words, the net belief is obtained when one rule or the rule 1 confirms the hypothesis, but another rule 2 discounts it. So we will consider now a case when rule certainty factors have the negative sign. So suppose that certainty factor evidence 1 and evidence 2 is a negative, so negative 1. So then from the equation, so certainty factor 1, hypothesis given evidence 1. So our certainty factor evidence are both negative. So ito. So certainty factor for the evidence is 0.8. So negative 1 multiplied by 0.8. So we have 0.8. And then the certainty factor of hypothesis evidence 2 is negative 0.6. So kasi po both negative siya. So we will go with the third equation. So certainty factor of the both combine two pieces of evidence is equals to certainty factor of hypothesis given evidence 1. So ito po siya, which is equals to negative 8 plus certainty factor of hypothesis given evidence 2, which is 0.6. So kasi negative siya and then kailangan i-add. So different signs, so subtract. Multiplied by 1 and then the certainty factor of hypothesis given evidence 1, i-plus na naman siya, and then negative. So, minus. So, their product is negative 0.92 and the 0.92, negative 0.92 represents the incremental increase of disbelief in hypothesis. The certainty factors theory provides a practical alternative to Bayesian reasoning. The heuristic manner of combining certainty factors is different from the manner in which they would be combined if they were probabilities. The certain theory is not mathematically pure but does mimic the thinking process of a human expert. Comparison of Bayesian reasoning and certainty factors. Probability theory is the oldest and best established technique to deal with inexact knowledge and random data. It works well in such areas as forecasting and planning, where statistical data is usually available and accurate probability statements can be made. However, in many areas of possible applications of expert systems, reliable statistical information is not available, or we cannot assume the conditional independence of evidence. As a result, many researchers have found the Bayesian method unsuitable for their work. This dissatisfaction motivated the development of the certainty factors theory. Although the certainty factors approach lacks the mathematical correctness of the probability theory, it appears to outperform subjective Bayesian reasoning in such areas as diagnostic, particularly in medicine. And one example that we have give a while ago is the Bayesian expert system. Certainty factors are used in cases where the probabilities are not known or are too difficult or expensive to obtain. The evidential reasoning mechanism can manage incrementally acquired evidence, the conjunction and disjunction of hypotheses, as well as evidences with different degrees of belief. The certainty factors approach also provides better explanations of the control flow through a rule-based expert system. The Bayesian method is likely to be the most appropriate if reliable statistical data exist. The knowledge engineer is able to lead, and the expert is available for serious decision analytical conversations. In the absence of any of the specified conditions, the Bayesian approach might be too arbitrary and even biased to produce meaningful results. The Bayesian belief propagation is of exponentially complexity and thus is impractical for large knowledge bases. Application. Expert systems designed for medical purposes have been an integral part of the historical development of artificial intelligent expert systems. One of the earliest expert programs developed using list processing was a psychotherapist program named Doctor. As research continued, particularly at Stanford University and Massachusetts Institute of Technology, further rule-based expert systems were developed. At Stanford, an expert system called MySyn was developed to diagnose blood and brain infections and to recommend appropriate therapy, a system which proved to be as nearly as accurate as human physicians. The inference engine from MySyn, dubbed Essential MySyn, was used to develop many new expert systems. The root of most of today's medical expert systems are derived from MySyn.